Hi class, today we're going to be covering the atom, and this is chapter 4.3. So the atom is the smallest particle of an element that retains the characteristics of that element. We cannot see the atom with our naked eyes. We need a special instrumentation in order to do that. And I have seen an atom and it was still difficult to understand what I was looking at. So let me explain the definition. We have a gold bar and we have aluminum foil. Let's take a look at the gold bar. If we go down into think about layers and we keep going down and down and down, and eventually what we'll do is we'll hit a layer of these spherical little spheres, if you want to call them that, and that's the atoms. And now if we move all those atoms away and we end up with just one atom, if we try to break that atom apart, it is no longer the smallest particle that retains the characteristics of that gold. So we have one gold atom, and if we break it apart, it's no longer a gold atom. So that's the furthest that we can go down and still consider something part of the characteristics of an element. Same goes for aluminum. We do the same thing, and what we do is we end up with one aluminum atom, and we can't go further than that. So we ended up a bunch of people in the early 1800s and 1700s and so forth did a whole bunch of experiments, and based on their experiments is how we have so much information about the atom itself. And one of the people that really started this was John Dalton in the early 1800s. He did a lot of experiments, so it wasn't even about just the atom but other things in chemistry that we still the laws that he developed we still use today. So one of the main things here, though, is Dalton's atomic theory helped form the basis of a current atomic theory. And what he came up with some modifications compared to what he did. So we've expanded on it when we have further knowledge. But back at the time, he did pretty well with, think about, nothing with the technology we have today. In Dalton's atomic theory, atoms are tiny particles of matter, which we've already discussed in the first slide. Atoms of an element are similar to each other and different from those others. So if we look back here, all the atoms that are gold atoms are all the same. But all the atoms for aluminum are all the same. But they are different from each other. That's how you know you have a gold atom and you have a silver atom. They are different from each other, but they are similar with their own element. That's what that means. Okay, so the atoms of two or more different elements combine to form compounds. What this means is you take an element from the periodic table, for instance, hydrogen, and you combine it with oxygen, we end up with H2O. So these elements will combine together to create substances or compounds. Atoms will also rearrange to form new combinations in a chemical reaction. What this means, and we haven't gone that much further into this yet, atoms are never created or destroyed during a chemical reaction. This means that they have tested this in an isolated, think of a vacuum, where they can control everything. And what they have discovered is that the starting material mass that you have after a chemical reaction, you still have that mass after the chemical reaction, even though the properties, there's new compounds compared to what you started out with. So for instance, let's go back to hydrogen gas. We have hydrogen gas, and let's say we have 2 grams of hydrogen gas, and we have 2 grams of oxygen gas, and then we cause a chemical reaction. So now we have water. What they discovered is that we had 2 grams and 2 grams of hydrogen gas and 2 grams of oxygen gas, which made 4 grams of starting materials. But after the reaction, they still had 4 grams. It's just now in a different substance, but the hydrogen and oxygen still exist. So nothing is created nor destroyed. We really don't think about it because we're in an open environment, but in an isolated environment, they can test this, and they've proved it over and over again. So the atoms just break bonds and form new bonds, which creates new substances, but there's nothing new here. So they did further experiments, and they did these with electricity, and they noticed the behavior of the particles, of the subatomic particles. And they noticed that 2 of the subatomic particles had electrical charges, and they were opposite of each other, a positive and a negative. How do they know this? Well, have you ever played with magnets, and there's a positive side and a negative side, and when you try to put the 2 positive sides or 2 negative sides together, they repel. But when you flip one, they are attracted to each other. This is the same thing. They notice the same exact behavior with the experiments that they were doing. So they have two. So subatomic particles consist of three subparticles. One is a proton, and it has protons have a positive charge, electrons have a negative charge, and then they discovered even another one that had no charge, which was neutrons. And they follow the same thing. Like charges repel and unlike charges attract. This behavior gave them more information about subatomic particles. So now we got to Thomson. Thomson realized that he discovered the behavior of these particles. So what he did is he had these cathode rays, and you don't really need to worry about this stuff too much, and they contain negatively charged particles, and he shot them in a vacuumed space so there's no air, and he can control the behavior. And you see in this picture, which is a very poor picture, there is a positive plate and a negative plate, and what he noticed is that these negatively charged particles would repel on one side and be attracted on the other. So the behavior would change. And through this, he discovered what he called the plum pudding. I have never seen plum pudding. I don't know what plum pudding is. In all these years, you would think I would have looked this up by now, but I have not. But it doesn't matter. We're going to show you a picture of supposedly of something. And what he proposed is a model in which the protons and electrons were randomly distributed in a positively charged cloud. So the way that I envision this is like a chocolate chip cookie. They're just randomly wherever. You cannot control each cookie and where the chocolate chips would be placed. So that's what he determined, that it would look like this, which I'm going to take a step back. This is a very bad picture. I found this on the internet, and when I pulled it up, it did not look like this. This stream here is got electrons in it, these negatively charged particles. And what he did is, if you put a magnet, you can see now that the behavior either will repel or be attracted to the negatively charged particles will either be attracted to the magnet or repel the magnet. So I just wanted to show a picture of that. So what he decided is that there's got this plum, or the purple part is positively charged pudding. So I think of it as positively charged dough. It's just there, it's positively charged, it's just a blob, and then you've got these particles just kind of wherever around it, and that's it. It's just mostly a mass of empty space in a sense. But Rutherford and Thomson from the previous, they wanted to expand on the experiments, and they were going to do another experiment to further prove the plum pudding. But what they got was something entirely different. So Rutherford set up a gold foil, and he shot particles at it, positively charged particles. And what ended up happening, or what they hypothesized was going to happen, was these positively charged particles would just shoot right through and come out on the other side of the thin foil. Nothing would happen. But that's not what happened. There was a few particles that acted like they hit a wall and then went 180 degrees back. So something was blocking them, and that made them have to reevaluate what they were thinking of, because this wasn't what should have been happening. If it had ran into electrons, it should be attracted to it. So something was wrong. And what they discovered, so I found this little GIF here where you see, I think the one hits right here, and it will see they bounce back, and they're hitting a densely charged part. So what he concluded is there was a small, dense, positively charged nucleus. So in the middle of each atom, there's a small, densely, positively charged center. And so Thomson's theories here, Rutherford came up and he called it the nucleus. So in the center is where it's positively charged. And that would explain why most of these positively charged particles went straight through an atom, but very few of them would deflect, but they still deflected, and they had to determine what was going on. So now we get to the structure of an atom. So based on all these experiments, this is now what we have concluded the structure of an atom is. So an atom consists of a nucleus, and that in the center of the nucleus contains the protons and the neutrons. And then on the outside of this is the electrons. The electrons are on the outside, but they are not very close. So most of an atom is empty mass. So if you think about it this way, the nucleus would be a baseball put in the middle of a football field. And most of the football field is where the electrons are. Yes, this is We cannot see this, so this is on such a scale that we can't even imagine. But if we had to put it into how we can think of it, that's one atom. There's a baseball, the protons and the neutrons are in the baseball in the center, and most of the empty space is where the electrons are located. And what they also discovered is the mass of the atom, most of the mass, all the mass is from the protons and the neutrons in the middle. So that baseball holds all the mass, and the electrons are so small and the weight is so different that they just don't even include them. So this just repeats everything I said, that we take a look at lithium here, we get it to the atomic scale, and then we break into the subatomic, we break one open, and you can see the nucleus, you can see the electrons, and most of the mass is here, and that's what it looks like in there. And the electrons are moving around very, 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 very quickly. So this is kind of a depiction of it, and that's why you see this. So mass of subatomic particles are so small that chemists came up with a certain unit called the atomic mass unit, AMU. And one AMU has a mass equal to 1/12 the mass of a carbon-12 atom. That contains 6 protons and 6 neutrons, which at this point you really have no idea what that means. And don't worry about that too much. It's something you have to know. It's in the book. I'm not going to really ever test you on it, except for I might ask you what the mass is equal to. So you should know that, but don't really go more into this. Don't stress yourself out about it. 1 AMU is equal to 1 Dalton in biology. And again, electrons are so small in mass that they just don't even include them. How small are they? Well, if you look down here, you can see that a mass of a proton and mass of a neutron are almost identical. And then an electron is just got so many zeros that they just don't even count it. So a proton has a positive charge, so they count it as a 1 charge. A neutron has a 0 because it's got no charge to it. And an electron, they count it as a -1 charge. And the nucleus contains the proton and the neutron, and the electron is outside. And this is how we write them, either a P or a P plus, an N and N0, and then electron's always an E with a superscript of a dash. We don't tend to use AMU. We will, but very rarely. What we do with conversions and so forth are we use grams. So you can see even with grams, these are very close to each other. They have -24, which is still hugely, ridiculously small. But electrons are even smaller. They have -28. So let's test the knowledge about this. Which of the following subatomic particles fits each of the descriptions? So found outside the nucleus. Well, I pointed it out here, and it is the electron. Has a positive charge. Think of P and P. Its protons have a positive charge, and then has mass but no charge, and that is neutrons. And we're going to get more into masses, so believe me, you're going to get really comfortable with this stuff really quick. And that's it. Thank you.